I want you to make your best estimate as to the dimensions of a 1 litre container. So how high, how long, and how deep would that container be? You might think about some things you know, like a litre of milk, and your answer needs to be in centimetres. So write down the height, the length, and the depth, and I will reveal later in this video how close you got to the correct answer. The next step in this lesson is to give pairs of students either 24, 48, or 96 linking cubes, depending on their ability, and get them to see, with those cubes, how many different rectangular prisms they can create. So this is not a prism because you can't slice it and get consistent looking pieces. As students discover each new shape, they should draw a diagram to record that somewhere. They might, if they're thinking logically, be able to use this insight to discover new shapes. So if I broke this in half here, I can now put it that way and I've got an entirely different shape. I've chopped that in half that way and then put it over here. So I've doubled the dimension here, the 2's become 4 and the 12 has become a 6. So now my shape looks something like this. 1, 2, 3, 4, 5, 6. And even getting kids to draw this, you'll find that a number of them struggle with something like this. You can see I'm struggling there with my 3D shape. Anyway, that's a 4 by 6 by 2. If your students are really clever, they might have put down a table. And if they haven't, this is your chance to show them how you can use a table to collect all of the shapes that you can make. Many students will begin their investigation with the ridiculous 48 by 1 by 1 stack, which works, but it becomes a bit unwieldy. So we'd record this in a table, and the advantage of a table is we get to see the information really clearly, and we can then use this information to generate new things. So, if we know that a 48 by 1 by 1 works, we can halve the 48. So we can break the tower in half and make it half as tall. So it's like snapping this in half and then putting the 2 halves side by side. And now our tower is going to be only 24 units, 24 cubes tall, and either the length or the depth of the tower will be doubled. We can decide which one, but it'll be the same thing either way. So if we put double the length of it, it's going to be 24, 2, and 1. Now the total amount of cubes we've used for every tower will always be 48. And there might be something your students begin to notice about these numbers here. We can halve it again, and we can get 12. And then we can double the length or the depth again. And this time we'll get a unique shape if we double different ones. So if we double the length, we're going to get a length of 4 and still a depth of 1. Using 48 cubes, or if we doubled the depth, we would get 12 by 2 by 2, and that will also equal 48 cubes. Then we might divide by 3. Now this is using some algebraic thinking, because if we're dividing the height by 3, something else has to multiply by 3 to keep the number of cubes the same. Otherwise we've just made the tower a third of the volume. So we're going to divide this by 3 now. So we're going to get 4 here, and then one of these needs to multiply by 3. So we'll multiply this by 3, so 4 by 6 by 2, 48. And hopefully by now, and if they haven't, you can point it out, your students have recognized there's a bit of a pattern here. If we put a multiply sign between each of these things, that's going to make the number 48. And that is how we calculate volume, by working out the height, the length and the depth and multiplying them all together. Now, this is important for the 48 cubes, but this was building up to something that's really far more interesting. After you've discovered every option, you can get students to choose one package that they would like. And then we're going to calculate, if you want to go down this rabbit hole, the surface area of each of these things and work out whose package requires the least amount of wrapping paper. Some students might be able to use their shape or a visual representation of their shape to calculate the total surface area in squares. Other students might need a scaffold of having the net drawn up or drawing up the net themselves and then calculating all the surfaces and how many squares you require. Now, the fascinating thing about this, which will lead to our next discovery, is that the most inefficient package, a 48 by 1 by 1 package, takes 192 square units to cover in wrapping paper. Whereas the most efficient, well, the most efficient using whole numbers anyway, is a 4 by 4 by 3, which only requires 80 square units of packaging. So less than half the amount of packaging. Now I need you to take the three numbers you wrote down earlier for your estimate and multiply them together. So for example, 10 times 8 is 80, 80 times 5 is 400. This is how many mils your container will fit. So if your number ends up at 1,000, you've got it spot on. I, in this example, was way off. What this means is that this here is exactly 1 litre, 10 by 10 by 10 centimetres. Pretty surprising, I've never seen a milk carton look like this. Now you might think of some reasons why a milk carton doesn't look like this, which we'll get to in a second. But what this also means is that this little wincer here, that is 1 mil. It means this is 10 mils, and it means this is 100 mils. Pretty logical, right? That metric system. So even though this is the most efficient way to make a package that contains 1 litre, I don't think we'll ever see that in our supermarkets. The reason, I think, is 1, maybe it's a bit hard to pour, but 2, branding. If you've ever gone to a library and selected a book, it's very likely that you've selected a book not that looks like this or is presented to you like this, but one that is facing this way. And you can see the whole cover. And I think brands, even though they're going to use more packaging to put cereal in, are going to continue to do this so you can see what you're looking for. So we can arrange 1 litre in different ways, just like we did with the cubes earlier. We could replace it with 1,000 of these and make 1 litre that's 1,000 centimetres long, 1 centimetre deep and 1 centimetre wide. We can also replace the yellow block with 10 of these bad boys. And if we do that and lay them out on the ground, 1 litre can become 1 metre by 10 centimetres by 1 centimetre deep. So that's helpful. And if we had a knife, we could divide this again by chopping one of these pieces into tenths. We could make this 10 times wider. So we'd make this less deep by 10 times the amount, and then we'd make it 10 times wider. And I'll lay that out for you, and then we can see what it would look like. I'll fill the outside now, but you'll have to imagine the inside's filled. What this means is that a 1 metre by 1 metre by 1 millimetre container has a volume of exactly 1 litre. Now this is fascinating because if we get 1 mil of rainfall on a metre squared of roof, that puts 1 litre into our tanks, which leads us to our final fascinating discovery. You can use Google Maps to find your house and work out how much water 1 mil of rainfall would deliver if you've got tanks. Now, I'll just zoom in here to our house. And if we zoom in, you can change the view. You can see that we've got some tanks there. And so we'll go back here. And there's this little tool. I'll zoom in one more. If you right click when you're on Google Maps, it'll bring up this thing and allow you to measure distance. And then if you left click, you'll get the distance between the 2 points. So we can clear that distance after we've got that. So we'll measure that 13 and 0.79. So we'll clear measurement, and then we'll do it again here. So measure distance and then go to here. So about 10 meters. So, 17.92. So when you multiply those two things together, you get roughly 243 square meters. So that gives us the big rectangle here. And because this is a compound shape, we're going to need to figure out the smaller rectangle here. If you wanted to get it really accurate, you'd break it into triangles or something. So I'll clear the measurement and go again here. So we've gone measure distance here, about 6 meters. And if we clear that and then go again from the top here, across to there, about 11, so 66. Add those two bits together, and the total square meters for our roof, 309. So for every mil of rain we get, our tanks get 309 litres of water. Now, if students are feeling a bit nervous about measuring their own house or revealing where they live, then fair enough, they can do a Bunnings Warehouse or something else, see if they can find the roof that holds the most amount of water. Enjoy the activity.